from there. And as I say, we're at the University of Strathclyde in Glasgow in the UK. So I'm a professor of smart grids. I hold a chair that is sponsored by Scottish Power, one of our main electricity companies in the UK. I'm also co-director of something called the UK Energy Research Centre, or UK ERC. And it's really through that, which is a kind of multidisciplinary, multi-university centre trying to address questions arising around the energy transition, that I've got involved in this whole question of multi-energy system analysis. What we're going to talk about is the growing need for this kind of modelling, and then Graeme in particular will dig into some of the things we need to think about when extending our kind of system modelling to multiple carriers. Think about what we're using a model for, how we structure a model, some of these kind of design questions around modelling to do with the spatial and temporal dimensions, you know, kind of avoiding being bogged down in excessive complexity, how to treat uncertainty and so on. And then hopefully, if I get on with it, we'll have some time for Q&A as well. So for me, the kind of main objective, the main motivation for doing a lot of this is about emissions reduction. We've known about the greenhouse gas effect for 50 years, really. The evidence that points towards it has been growing. It's pretty blooming strong, actually. And 5 years ago, the Conference of the Parties, the COP, that met in Paris, the 21st such Conference of the Parties, agreed a set of goals for the world in terms of limiting global temperature rise to significantly less than 2 degrees C and trying to limit it to 1.5 degrees C. So we need to take some pretty dramatic action in terms of greenhouse gas emissions to achieve that goal. Because the impact of climate change, I mean, already we're seeing it is getting pretty severe in many places. We're definitely already on that path towards 1.5 or 2 degrees C. We don't want to go any further than that. Action is needed in every sector of the economy, and that's going to have a big impact. But certain sectors are particularly hard to decarbonize. Aviation, for example, shipping, certain parts of industry. And in terms of the trajectory for getting there, there are all sorts of trade-offs that need to be decided. Which things do we do first, which can come later? And it's really in trying to understand all of these trade-offs that we need to do this multi-energy system modeling, and also to be sure that there is kind of resilience of an energy system, the ability to prevent, contain and recover from interruptions to supply is not compromised by these changes to the sort of assets that we're using. I mean, and given that we're changing these assets, in particular for us as power system engineers, we know about this very well. Getting rid of thermal plant and the synchronous machines that go along with it. What new services are required on the system in order that the power system can remain stable? And a lot of that will involve the use of flexibility from the demand side, as far as we're concerned, on the power system. For example, flexibility in heating or cooling, or in demand for energy for transport. This transition needs different kinds of physical assets. They need to be built over the next 10, 20, 30 years. Old assets are going to be retired. And we need to work out how to optimize these assets once they're built. How can we operate them together? And by looking ahead to see how they would be operated, that helps us to decide which ones really need to be built, what kind of backup we require, what contingency reserve, and so on. And that in turn raises some big questions about how are they going to be paid for? Who is actually going to invest in building and operating these assets? What kinds of regulation are going to drive it? Are there some sort of limits around their operation? What sort of incentives or commercial structures? So all of these things, I think, come into the scope of multi-energy system modeling and help to show why we need it. Now, what you can see now on the right is the output of a multi-energy system model. Actually, we would call it a whole energy system model, and Graeme will flesh that out, that subtle distinction a little bit later on. So we set up various scenarios. Now, there's a bunch of things to the left of that figure, GHG 80. That's with an 80% reduction of greenhouse gases set as a target to be achieved by 2050 relative to 1990 levels. On the right, you can see some more stretching targets. So you can see one for, that's the greenhouse gas reduction of 80% by 2050, but others of 85, 90, 95, and 100%. And you can see some of the differences there and how it's sort of squeezing particular sectors much harder to get the emissions further reduced. Now, one of the things that I think is maybe you could say is kind of curious about this, it's almost maybe a modeling artifact. This has come out from an optimization which has been set a constraint in terms of the emissions and trying to meet it at least cost, given a large set of data on the energy services to be delivered and what all the various technologies are, the relative costs and emissions. And as it squeezes harder and gets a bigger reduction, it's actually squeezing particular sectors. So it eliminates, for example, going from sort of left to right, all emissions from the residential sector, but seems to leave the transport sector alone. Why should that be? Is it really so obvious that it's going to be much better, like do everything in the residential sector and leave transport? Well, actually, I think the costs are so close together that maybe that's not actually the right kind of answer. And especially when you look at it in the light of the uncertainties about what those costs really will be. This is a change that is already happening. Hopefully, you've seen this kind of diagram before, known as a Sankey diagram. So it shows energy inputs on the left and these end uses on the right. What's down at the bottom are exports. So this is looking particularly at the UK energy system, or also at the bottom are losses, for example, in converting from fossil fuels into electricity. Now, in terms of where electrical energy is coming from, these are the inputs and how much energy was coming from different sources in 2012. A lot of coal in that mix. If we wind the clock on to 2018, we can see that the amount of coal being used for electricity is dramatically reduced. So from an emissions perspective, that's fantastic news. However, there is a lot further to go. We still need to meet the demand for energy services, but it would help in meeting this whole challenge of reducing emissions if we can reduce the amount of energy used while still meeting the service. So the service in terms of heating, cooling, mobility, lighting, and so on. So energy efficiency is a really important thing. And we still have a long way to go in terms of reducing the fossil fuel use. So the unabated use of hydrocarbons is not something that is acceptable in 2050. So there's a lot of work to be done to find out how to meet that energy service demand without unabated use of hydrocarbons. Now I say unabated, we could be trying to capture, we could still be burning those hydrocarbons and trying to capture the CO2 that comes off and then store it somewhere over kind of geological timescales. And again, especially in terms of meeting that in-service demand, I think for us in the UK and many other parts of Europe and North America and so on, there are especially big challenges in heating and transport. Now, you may have come across this sort of formulation, this framing of the problem before, which is maybe it's a bit old hat now, actually, known as the trilemma. Some people have moved on to thinking about the 3Ds, but I think this is still useful, this trilemma. There's a tension between this goal of decarbonisation, which actually we might set in a model, as I said earlier, as a constraint, and doing it in a way that's affordable. In other words, this is maybe the objective function of an optimization, of minimizing the cost. But we still have to meet some kind of reasonable expectation of reliability of supply. We can meet demand. Now, okay, there's some detail in there about, well, what is the demand anyway? How much of it is flexible? What are the consequences of not meeting it? But I think we can understand this framing in kind of broad terms. Although actually, I think it goes beyond that in terms of public acceptability. There are different sorts of things that we can see already are kind of more popular or less popular. And it's not just that the total cost is minimized, it's also a question of where the cost lies, how it is spread across society, who benefits and who has to pay. Public acceptability, we see objections to the building of overhead lines. Some people don't like wind turbines. Other people are objecting to a nuclear power plant. But there's an impact on the wider economy in that it's not just a cost. I think most estimates would say, yes, there is a cost. A recent study in the UK suggested that this decarbonisation by 2050 would cost between 1% and 2% of GDP. This money does go somewhere. It does create jobs as well. So there is a green economy that is growing and is becoming of increasing interest. So yeah, there's a wider impact to think about. But for us as engineers, serving the wider society, we've still got to make sure that the system will actually work, that it is stable, that it is operable, that it can be maintained, that we can meet that requirement of a reliable supply. Now, the trouble is, all of this involves some huge changes. The whole economy, lots of physical assets, very expensive. There's lots of things to think about in terms of public acceptance and social attitudes. We can't experiment with those things really before we commit to pretty dramatic changes. So we need models. We have to understand what the implications will be before we commit to them. So just to kind of illustrate some of these challenges in a bit more detail, here is a time series of demand for energy in Scotland, which is a part of the UK. We have 5 or 6 million people living in Scotland. So we're accustomed to the temporal variation of electricity demand. But on what kind of scale does that happen? Well, that's the red line on that figure. There's 2 other lines that I draw your attention to. So the kind of blue line is demand for gas. And in Britain, we use a lot of gas for heat. So I think about 85% of our heat demand is met by burning methane, natural gas. And the kind of more blocky lines, that's sort of monthly demand for energy for transport, so especially for vehicles on the roads. So you can maybe get a sense of the scale. We've got to decarbonize heat and transport. What are we going to do? We're going to electrify all of it? And what happens if we do? So we did a bit of an experiment here with a colleague at the University of Birmingham to look at, just to begin with, converting half of that gas demand to using heat pumps with a coefficient of performance of 3. So electric heat pumps are very attractive because you can get more energy out than you put in. And that's what we see to the electricity demand. It goes up significantly. Now that daily energy use goes up by 50%, but the kind of hourly peak will be going up by more than that. But of course, we can see a big intra-annual variation. So how big do we need to build the electricity system? How much generation capacity, how much network capacity to meet that variability? And how much can we expect from flexibility? Transport is another kind of key challenge, I think. So one thing that's kind of interesting is the fact that actually cars, certainly in the UK, and I expect it's quite similar in other places, maybe not quite the same numbers, spend a lot of their time parked, not actually moving. So 3/4 of the time parked at home, other time at work or in public places, left with sort of 4.3% actually on the road. So if we're talking about electric vehicles and how they might be charged, they could be plugged in for a lot of the time. How much energy are they going to need to replenish what's been used in driving? Well, okay, we could, just to get a bit of a first handle on this, we could look at the average. An average mileage, how much energy would that use? Electric vehicles, fortunately, are more efficient than combustion engine vehicles. So if we had that plugged in at home, just that 76% of the week, that's a pretty low average charging power. Not much bigger than your average fridge. And I'm glad to see that that fridge is full of healthy things rather than just beer and wine. So in theory, there's a lot of potential for flexibility if these vehicles are plugged in. But of course, there's also a big spread in how much energy you need to put into the battery in order to replenish it. And then, of course, in the charging power as well. Okay, now that's just heating and electric vehicle charging. What if we put the 2 together? That becomes even more of a challenge. This is just a bit of a time series study looking at just a few buildings. Not much diversity of demand, I suppose, in this particular case study. But if we look at an electric heat pump demand, that's the red line. And then this blue line, it's a sort of a dumb charging, just assuming as how many people are arriving home in the evening and just plugging in straight away and just charging their vehicles immediately. You can see there is that evening peak, which adds up to an evening peak that we see ordinarily in the UK anyway, but it just makes it significantly bigger. With smart charging, we can try to spread that out a bit, leave some of that EV charging to later through the night in order that the peak demand is not exceeded. But we still have that peak now being determined by the heat demand. So that becomes the kind of critical factor. Is it very easy to move that around? How much diversity can we expect? Well, one thing is that typically everyone experiences the same weather at the same time. So, okay, we can imagine incentives for smart charging, but how do we provide flexibility in demand for heat? And this is the kind of thing now that we're trying to explore using this multi-energy system modeling. One of the things that can give us flexibility is sort of hybrid technology. So some kind of heating plant that has the choice between electricity or gas. Or alternatively, it might be burning gas and it could produce an output that is heat or electricity. So feeding electricity back into the system to help meet the local demand. If you've got, for example, a distribution network constraint that you have to operate within. Then the question is one of optimal operation. Knowing what the time series of demand will be for heat, for electricity, knowing what all the different demands on a particular bit of the network are doing, how can we operate this particular asset? It's a bit of modelling that Graeme has done with some colleagues at UCL, the University College London, and we can see how gas boiler output is topping up the sort of air source heat pump output, particularly when it's cold, on those colder days, when you can't get enough power from the electricity network. But the downside of that is there are extra capital assets to be installed because you're going to have a gas boiler as well as an air source heat pump. And that's as an alternative to spending money on the electricity network, upgrading that. So what is the right option? One of the things that people have talked about as well a lot, and it comes and goes as a topic, but again, I think it's on a bit of an upswell at the moment, is about hydrogen as an energy vector, and particularly to do with the flexibility that it gives you. Thinking back to that time series of heat demand and how much bigger it is, of course, in the winter if you're in one of the kind of colder areas. We've got the possibility of making hydrogen all year round, storing it, and then using it either for transport or for heating only when it's needed. Now, for transport, it seems attractive for heavier kinds of vehicles. So, lorries, maybe for trains on sections of track that don't have overhead lines. Still the jury's out a little bit on whether it's useful for smaller vehicles as an alternative to batteries. But we can see it there as a use in buildings and in heavy industry, which need very high gradient, high temperature heat, intensive heat. Again, it looks like an attractive option. We've got two ways of making it. We can have steam methane reformation or autothermal reformation, the latter being a slightly more advanced process, but by which you can capture more of the CO2. This is absolutely essential that we can do that if we're still going to meet these emission reduction targets, or via electrolysis. Now, the analysis at the moment suggests that reformation is cheaper, but we'll see how that market for electrolysis goes as it grows and manufacturers get a bit better at what they're doing. But this is a question clearly about how all of this and the manufacture of hydrogen fits in with the electricity system. So already I've touched on a number of different parties that might want to be informed by this kind of multi-energy system modelling. There's questions about how you operate plant, and there's questions about then investment planning and then policy making. So you probably heard this quote before from George Box a few years ago now, all models being wrong, but some are useful. So we're going to be honest about how accurate we can be, and Graeme will talk about that in a bit more detail. Then we'll get other details more so later on in the tutorial. So yeah, plant operators want to know how to optimize the design and then the operation of these different systems when they're working together. What are they going to build? And they're kind of not just sort of investors in individual buildings and individual heat supplies, down from domestic consumers up to suppliers of energy for a campus or a commercial premises, shopping centre, whatever. But also, big assets such as carbon capture plant, the electricity network, the gas network. What is the future of a natural gas network if we're going to use electricity much more so, or natural, or hydrogen? But there's also goals for policymakers. Governments have signed up to the Paris goals. We are hoping that when COP26, the 26th Conference of the Parties, comes actually to Glasgow, to where I live, in November next year, that they are going to agree some proper, serious, nationally determined contributions to meeting this global challenge. They're going to have to decide what is the right way of doing it. How can they, as policymakers, drive investors to building the right assets and operating them in the right way? So quantitative evidence to inform policy and give politicians the confidence to sign up, knowing that it can be done, knowing that the costs can be shared in a reasonable way, is something that modelling is really important for. So especially that kind of quantitative modelling. Now, we have to be careful about how they're used and how they're interpreted. We have a really important responsibility, I think. And this cartoon on the right comes from a paper that just a kind of a comment article really that came out in Nature just last week, which is a really interesting read, I think. I think it's motivated largely by the coronavirus crisis and the various epidemiological models that have been used there. But the kind of policies might be kind of putting a tax on carbon, subsidies to different technologies, investment in R&D, kind of influencing people's behaviours and choices is a much harder thing. So what is a model for? Well, it's to build up the evidence base to give confidence to policymakers. But then what is a model anyway? Now, something I think we're accustomed to in power system analysis for years and years is the fact that we can develop a methodology, determine a set of equations to represent some phenomena. Yeah, we'll leave some out depending on what we're looking at. We can have a reasonable approximation. We develop the methodology, the solution algorithm. We debate it at this conference at PSCC. We can then turn it into some software. We can maintain it properly. And then this method can be reused to model different systems in different contexts. So the context is determined by the set of parameters and then the inputs that we give. This is not yet established, this kind of way of doing things of here's a methodology and then we can reuse it for different situations in this multi-energy system space. These models tend to be still quite bespoke actually. And so a lot of people working in this area think about a model as a particular combination of data and methods. And if it is quite bespoke, I think it raises some challenges that maybe we'll come back to do with maintenance. Okay, at this point, I will hand over to Graeme and stop sharing my screen and allow him to share his.
Okay. Thank you very much and good morning, everyone. I'm showing as unable to share my screen, so I don't know if someone needs to activate that for me.
Right, so we need to, crumbs, how do we do this? So Andre, can you give Graeme the right to share his screen? And meanwhile, I'll have a quick look on the Q&A while that is sorted out. And as soon as I see Graeme's stuff appear on the screen, I'll know we're okay. So Andre, maybe fallen asleep during my presentation.
No,
it's not happened yet. More, can I do it? No, I don't think I can do that. There we go. Technical challenges on the first day of the conference, everyone.
Well, at least we're the guinea pigs to get it all out of the way for the coming week.
So more, I can't see how to do that. Let me make a bit of a start. Graeme, I have got your slides.
Yeah, so if you just bring up my slides for me and I can nudge you to proceed.
So in the interest of progress, I'm going to shove that up there. Do that. And find the right one. That one, I think. I was going to say talk among yourselves, everybody, but no, do it quietly, please. Right. So can we all see that? So we can see energy system model is a big thing. Is that okay, Graeme? Yeah,
that's good. So thanks, Keith. As Keith said, I'm a researcher at Strathclyde who has spent the past several years trying to do some of this multi-system modelling. So I'm going to talk a little bit more detail about some of the challenges and difficulties of actually doing this modelling in practice. And I've also had the fun of trying to inform policymakers with outputs of models. So I've done some work for the Scottish Government in recent history, which also given me a little bit of insight into how you need to consider the design of the model when you're thinking about how people might use the outputs that you're producing. So as Keith has mentioned, there are essentially two main areas of investigation that are within scope, and we have multi-vector, multi-carrier models that combine representations of different discrete energy carriers into one single simulation or optimization. And you might hear multi-vector, multi-carrier, multi-energy. These are all basically different terms for the same thing. And multi-vector historically is the most popular term, but multi-carrier has become more common to avoid that kind of reuse of a mathematical term. But they mean fundamentally the same thing. But there are also a kind of older field of investigation, these kind of whole system energy models, where you're trying to characterize all the flows of energy into and out of a specific bounded system, often a specific country. So these kinds of models are often used to analyze decarbonization targets, like he showed at the beginning of his presentation. And if you've heard of models such as Mark Allen Times, these are kind of economic optimization models that try and do this entire system from primary resources through to end energy use. But the focus of this talk and this tutorials will mainly be around the former, but it's worth being aware of that kind of secondary investigation, because under the scope of decarbonization, there's more and more convergence of these two areas of inquiry as we look at how multi-carrier, multi-vector systems can help to meet a national decarbonization strategy. So if we go on to the next slide. So there's a few animations here, but we can probably push forward through them as you understand them. So if we are familiar, as we should all be, with power system analysis, if we are looking at a simple power system, then for electrical power flow, we're probably going to apply some kind of physical representation, something like Kirchhoff's laws, represent electrical losses, among many other things. And if we're doing an optimization in that system, then we might apply, for example, constraints around generated dispatch, try and do an economically optimal dispatch for that system. And we can do the same thing for other vectors. So if we instead model a gas network rather than electrical network, we can do equivalent constraints and set parameters. So we can, instead of looking at Kirchhoff's laws, we might do mass flow laws for those gases. We might look at leakage and thermodynamic losses in those pipes. And for an optimization, we might look at constraints around the inflows of gas into that system and line pack, so the pressure we have to maintain in the lines in order to keep the system operable. And if we model these separately, then they're essentially two separate models acting independently. And if you advance the animation, the interesting aspect of this is when we combine these two discrete carriers into one single coupled simulation optimization. So this can be from two main areas. So we perhaps have a particular location where we can convert from one carrier to the other. So perhaps an electrolyzer, which can be used to convert from electricity into hydrogen and inject into the gas network. Or secondarily, we can have demands which can be met by more than one carrier. So if instead of saying explicitly that a demand must be met by electricity or must be met by gas, we can look at how multiple carriers might be able to meet a single demand. If we go on to the next slide. And as Keith said, there isn't really a very standardized practice for analyzing multi-energy systems in the same way as we've established common practices in power system analysis. But probably the closest thing we have to that right now is what's known as the energy hub model. So this is a common framework within which multi-energy models are constructed. It's been around for about 15 years, where instead of looking at single carrier electrical buses, we might represent an energy system as one or more nodes, which has a set of carrier-specific inputs and outputs. And that node can have production, consumption, storage, and also technologies which convert between each of those carriers in some manner. So again, for example, like an electrolyzer, which can convert from electricity into gas. So you can then build up a series of coupled equations which represent both the carrier-specific equalities and inequalities, but also the conversions and the interconnections between them. An example is shown here for a kind of 3-node system where you have 3 CHP plants, combined heat and power plants, that can convert gas into power and heat output, connected to an external power network, supplying 3 electrical and heat loads. And then you can see how that builds up into a coupled system that you can then simulate or try and optimize in some manner. And you can do this either as a physical formulation, where you're looking explicitly at the physics of each system and trying to model as accurately as possible exactly how gas, electricity, heat would flow. Or you can do it more simply as a commodity flow. So you're treating all energy as identical, irrespective of which carrier it is. It's just a commodity to be moved in bulk from one location to another, or from generation to consumption, which simplifies things somewhat. So on the next slide, as an example of this, if we had a gridded system of nodes, so we might want to do a gridded based analysis if we're looking at an urban energy system, you would perhaps apply Kirchhoff's current law to the electricity network, but we have similar equations we can apply. So for the gas network, we might look at the mass flow law, and for a heat network, we might look at the thermodynamic coupling. And we have basically equivalent forms for each of these. So for the gas network, we're looking at the specific enthalpy of the gas and the mass flow. And for a heat network, we're looking at the heat capacity of the medium and differences in temperatures. We can see that even though the physics of each of those systems is slightly different, we can still come up with systems of equations that couple those together. Again, these are very bespoke, specific to the system that you're looking at, and I'm not going to go into more detail than that right now because the rest of the day will be full of examples of how to do this, but that shows how we build up these kind of coupled systems of equations. However, we can see that doing so, we're quickly going to get very complex models, potentially with very high dimensionality, and we need to balance this with the other demands of our model. So if we have a system that we're trying to look at very high temporal complexity, and we're also looking at high spatial complexity, and we're also wanting to look at big techno-economic detail, so perhaps including integer variables rather than just a straightforward linear optimization, and we're also trying to do multiple sectors at once, we end up with extremely complex models that can be very hard or almost or even impossible to actually solve in any tractable manner. So one of the challenges we have in multi-energy modeling is understanding this challenge of breadth and depth. How accurately do we actually want to represent each sector? How broad should the modeling scope be? And hence, where do we set initial and boundary conditions for our model? And especially if you're trying to represent all the physics of the different sectors, it can be very hard to include that. And if there's any non-linearities in the system you're trying to model, that makes things even more computationally complex. And so if we're going to have to do some kind of compromises in a multi-energy model, then this means we also should bear those in mind when we come to interpret the results of the model. So if we look at these issues of complexity, there are various options available to us in how we try and reduce this. These will be familiar to people doing power system analysis alone, but they just become more relevant as we're dealing with higher dimension models. So we can parallelize the problem, we can try and decompose it into sub-problems that can be solved separately and simultaneously. If we have high resolution in the temporal domain, which is very common for these kind of models, then we might seek to reduce that in some manner. And this graph on the right shows an output from an interesting paper which looks at reanalyzing the same system with multiple different time resolutions. And you can see for this example that as that temporal resolution is reduced, you greatly reduce the computation time required to solve that model, but don't have that much influence on the actual output of the model until you start getting to very low resolutions. So a solution can be to take a subset of your model and just to check if you adversely impact the output just based on the resolution that you're using. And there are other methods as well, so you can use heuristics, looking at minimum maximum periods, mask periods that you're not interested in at lower resolutions, use clustering techniques, that kind of thing. We also need to deal with spatial complexity, and again, that's a balance between the other dimensions that you have. So these big whole system models that we're talking about are often single node models. They don't have any spatial element whatsoever. We can look at reduced sections of technology, and again, we can reduce our model down to commodity flows of energy rather than physical flows to reduce that complexity further. And one thing to be wary of when we're doing this is if we're looking at multiple sectors, we have to make sure that we're treating them relatively equivalently. If, for example, we run a power system model that has extremely complex physics and every constraint that we might want to cover in the power system model, and couple that with a gas model that has no such constraints and is just a straightforward commodity flow of gas, then we might be artificially pushing the model towards a certain form of dispatch that just reflects the complexity we've introduced into the model rather than the fundamental system that we're trying to analyze. And I'm sure people will come along to this later in the day, but stochastic methods in these high dimension models can become extremely onerous as well because you're further complicating the system. One further thing to bear in mind is that, as Keith mentioned before, there is a difference between carrier demands for energy and actual energy service demands. So in single carrier models, traditional power system models, we would just define a demand for electricity, for example, and have a time series of demand that has to be met. But in a multi-carrier model, we may instead be interested in exploring how that demand can be met from a variety of resources. So if we define demand specifically as one carrier, then we might be artificially limiting the scope. So we might be more interested then in energy service demands rather than the carrier specific demands. So in the case of a heat system, for example, we need to treat demand at the service level because then we can compare the different technologies. And so if we understand what the demand for space heating, demand for hot water is, we can look at how those might be supplied differently through different carriers. But if we're looking at perhaps demand side response in our models, then we need to go a level further than that. We need to understand what actually creates those demands for services and what the behavioral and physical drivers for that. So for example, in the case of heat, we would need to understand the range of comfort levels of people living in buildings and how that interrelates with the building thermal envelope. Next slide. So this means that the multi-energy models that we're looking at may have fairly significant scope. They might go quite far outside what we would normally treat as an energy analysis. And this means, as I said, we have on the right things like energy service demands rather than carrier demands, but we're also getting into spaces such as interactions with the environment. And this is an increasingly significant area of interest in up-to-date research. So there are more and more models these days on how energy interacts with, for example, the water system, as different forms of energy production resources use different volumes of water, but also into how we interact between different countries in requiring different resources, so trading and availability of natural resources that are at the top end upstream part of the system. Next slide. So one other way to deal with this very broad potential scope is, of course, to soft link between models. So rather than trying to couple across the entire scope of analysis, we instead utilize multiple models and use outputs from one model as an input to a second model. Within the scope of power systems, this would be perhaps evaluating the outputs for economic optimization in a generation investment model, and then testing that in a power system adequacy model to make sure the system can actually operate. But in a multi-energy space, we might instead look at using an economic model to derive those energy service demands, use multi-energy analysis to derive what the optimal supply of those services might be from different carriers, and then to analyze the carrier-specific flows, perhaps the electricity flow and the gas system flow, within vector-specific analyses that then checks that we have a fully operable system. So we can then ask what the contributions of a useful model might be. And again, this comes from some of my experience of trying to interact with the policy space. And I think often as academics, we're principally concerned with creating new formulations that stand a good chance of being published without necessarily considering the full external value that the modeling can provide. And there's certainly multiple means by which a model can provide useful evidence without necessarily having to give significant novelty within its own kind of modeling framework space. And it also, within the potential complexity that we have in multi-carrier modeling, it would seem useful to reuse existing methodologies as much as possible. So I've given a list here of things that could possibly be used that aren't just about a new framework, but also saying that we can demonstrate existing technologies in new spaces, show how different technologies or policies compare to each other, and also how we contextualize and apply each of those possibilities. And next slide. So again, we can relate this sort of sense of usefulness back to the scope and the complexity of the modeling that we're trying to conduct. So a number of different phenomena within energy systems that we might want to evaluate, each of which are relevant to some different time frame. And we can perhaps look at multi-energy systems in lower temporal resolutions. So if we advance the slide one step, we can perhaps use that to analyze the design of a future energy system that's perhaps meeting a future decarbonisation target, but then complement that analysis with carrier-specific modelling on higher and higher temporal resolutions that determines if we're resulting in a fully operable and secure system. And for my last slide, if we're looking to conduct some useful modelling, how should we proceed with this? So we put together this kind of idealized framework for how we think people seeking to do modelling in this space should proceed. And the first step, of course, is to accurately define the problem, both in terms of the questions to be answered, but also setting the bounds and scope. And then secondly, select a modelling framework that is useful for those questions within that scope. Define how you'll capture uncertain and unknown parameters, scenarios for that model, and then move on to finding data, which can itself be a significant challenge if you're trying to match up multiple vectors. And certainly availability of data in fairly new areas of investigation can be very difficult to achieve. We would also seek to reduce the number of scenarios that we have, so we get the kind of key comparative outcomes. We reduce some of the complexity that we're trying to deal with, but while making sure that we get some insight into uncertainty. And then last, present the results of that modeling within their local scope, the scope of the model, but taking into account how that interacts with the external world. And one problem we often see is that modelers in the academic space often begin with the model before deciding the problem. So people in academia may come in at the design phase and they have a framework already in mind to use, or even have a fully parameterized model already available and not entirely sure what it is that they're going to do with it. And it's always worth considering that if the output of a model is providing evidence or supporting some form of real world decision, what is actually being proposed is actually actionable. So is there a single system operator that actually has authority over more than one energy vector? Is there a regulator that has the kind of oversight that you're looking for? And do people in these different sectors actually talk to one another? I think if you advance the slide a couple of points, then you'll see that highlighted. So perhaps at this point, I can bring Keith back in to look at some of these kind of issues when we look to implement models, what their place are in the world, not just within the academic environment. So if I can perhaps ask Keith who he thinks is using multi-energy models at the moment and who should be using them.
Yeah, well, I think both you and I have interacted with policymakers. You know, we've done some work with Scottish government, and we know some people in the UK government who are trying to use some of these multi-energy system models to look at potential pathways towards 2050 and decarbonisation. These are difficult models to use because they're very data hungry, actually. I mean, normally the way that they're formulated is quite simple, a simple kind of linear optimization with this emissions constraint. It takes a bit of care to know how to interpret them, I think, you know, as well as building it up. I mean, what's your experience of, you know, because you've spent some time in the Scottish government, Graeme, you know, we're working with some people who are using times models. Mm-hmm.
I think that there is obviously a desire within the policymaking world that output should be as simple as possible, which is a significant challenge when, as I've highlighted, these models are by nature highly complex, and presenting uncertainty in particular can be very, very difficult. And you always have this issue that people home in on the sector that they're particularly interested in. If they see any single weakness in the bit they're most familiar with, they interpret that as weakness across the entire scope of the model.
I think you might imagine that even today, gas and electricity system operators would be somehow understanding each other's systems and how they impact one on the other. You know, so there's a lot of gas demand that comes about from, you know, generating electricity, and I think there is still, I mean, we've seen this in other countries as well, still combined cycle gas turbine power plant that are on interruptible power contracts. So at a time when it gets cold and there's a high gas demand, suddenly you have power stations stopping operating, which come as a big surprise to the electricity system operator. I think we saw that in the kind of polar vortex in New York a few years ago. So maybe these kinds of people should be looking at the interactions, but what's stopping them? I mean, one thing might be some of the regulatory structure. You know, there is an electricity system operator, and then there is a gas system operator, and somehow they're kept separate, because maybe in the minds of some regulators, gas and electricity are in competition with each other, and therefore should not be seen as colluding.
And we can see that, for example, ENSO-E and ENSO-G are now producing joint scenarios for this kind of analysis. So trying to make sure there is commonality between the two sectors. That means that any analysis that is going on can be working on a consistent view of the world, as it were. But this kind of highlights the issue that it can be very difficult to actually get good data that builds up that strong picture that's complementary across all sectors. And data is never as open as we would like it to be. Yeah,
and I mean, Graeme, you're more hands-on with building these models than I am nowadays. Should we be are there particular practices we should be thinking about model maintenance? Is that possible to do when you're still prototyping the methods?
Oh, absolutely, and I think there are places we can look to for good practice in this. So the software world has many already established strong practices in documentation, in how you actually audit what you're doing. But that should be a key part of the process, that often you can have very large data sets that you have to use in order to prioritize one of these models. And so you need to consider how you manage that data set over time, particularly if you're looking to create a model that's going to be reused in the future. So auditing, basically regularly revisiting data to make sure it's up to date as possible, particularly as costs of hybrid technologies are rapidly changing over time, and just making sure that everything is transparent so that your model isn't pushed just towards one erroneous input data point.
Yeah, one thing that bothers me sometimes is go back and check that the outputs of a model correspond with reality. It should be possible to calibrate. There's all sorts of kind of approximations and fudge factors. I see a question coming in on the chat, for example, about guidelines of choosing where to do your approximations and where not. So one way of trying, it's a judgment, I think. I'm not sure it's possible to sort of say categorically which things to emphasize, but especially today with energy use in buildings. I mean, it's notoriously bad that a lot of the sort of civil engineering based models or the physics models, when you build the building, it doesn't actually turn out to behave in the way that you thought it would from the model. So we should be updating the models and calibrating them properly, shouldn't we?
Yeah, absolutely. I think people sometimes, most people will come to this from a specific sector. A lot of people here will, of course, be coming to this from the power system, and hence will apply significant resolution and complexity to one particular sector they're familiar with and miss out on the detail from others. So you need to talk to your colleagues in other sectors. You need to understand, for example, how buildings interact with the network to make sure you're not introducing your own kind of disciplinary bias to the modeling that you're doing.
Yeah, and I guess that kind of leads on to a point about communication as well, about being honest with the limitations and in understanding what the consequences would be.
Keith, Graeme, so interrupt. I just wanted to sort of link to this modeling aspect. So there is a very interesting question in the chat about data and uncertainty. And actually, basically, the summary of the question is that uncertainty in one domain can actually impact significantly on all the modeling given interaction. So what is your view in terms of data uncertainty and modeling uncertainty in general, looking at one specific domain and then how that domain may impact on sort of whole system analysis?
I think it's just as Graeme was saying, it's about bringing the different discipline specialists together who can comment on, hopefully from their experience and insights on the nature of the uncertainty and the significance of it. I think a big thing for all of us is to be honest about the uncertainties. Now that's not a great message that, and we mentioned policymakers, they don't like to hear any uncertainty. They like to be given answers that are right and be persuaded that they're right. But actually that would be irresponsible, I think, for us to say that. So it's about honesty. It's not just, I think there's a big mistake that we sometimes make of saying, well, this must be right because my model says so. Well, actually, sometimes the uncertainties in the inputs, swamp, they're massively bigger than kind of the accuracy that we kind of are pretending to get from the modeling itself.
Mm-hmm. And from a practical perspective, I would add to that you can see this kind of penny switching behavior in optimization models. So you can often in whole system models get a result that just reflects the fact you've adjusted one cost to be very slightly lower than another one. And it may be unfeasible when you have a huge amount of technologies and cost inputs to actually flex and investigate the uncertainties in every single one of those. But it becomes key that when you do have an output, if your model is recommending heavy investment in a particular technology, that you then go back to the model and assess the sensitivities to those particular key inputs and outputs. And again, because we're talking about often technologies that are very new, very uncertain, this can have a very big impact.
So Keith, Graeme, while of course I invite you everyone to post more questions, I just want to ask you a quick one because it's pretty interesting. And this question you have on the bullet point, does it matter that data are realistic? So what did you mean exactly there?
Well, it's obvious, isn't it? It does matter, although it depends what you're doing with the model, to be fair. Some of the time what we're doing, I guess a lot of us in this conference are researchers. We're trying to develop new methodologies. In terms of testing our methodology, maybe it's not so important at that stage that we're modeling kind of a real system. We want to see, develop our understanding. So quite artificial models are good for improving understanding. Don't make them too complex, so you can have a sense of what's really going on and what's driving the outputs. But at some point, models, if they're going to make a difference in the real world, someone's going to have to act on the outputs. That's what we mean about something is actionable. Okay, a policy can still be sort of tweaked and adjusted, and it depends on lots of people's responses to it, which are hard to predict. Somebody mentioned on an earlier question about some of the behavioral aspects. But investment decisions, operational decisions are going to cost money, so we have to be confident that we're using the right data. So be clear about, okay, this is the stage of kind of testing our methodology, and this is the stage of application. And when it's becoming applied, then we have to be really serious about the data and serious about, how buggy is our code and how easy is it to be maintained.
And I think that isn't to say that it's only worth doing if the data is realistic, because there's lots of novel areas of investigation in multi-energy where we just do not have good data or good understanding, but doesn't mean we can't demonstrate concepts. So I mentioned before about things like interaction between energy and environment, and that's a fairly novel area of investigation. Very hard to do because, again, data sets that are good for that can be very hard to come across, but it doesn't mean that there's no value in exploring the potential impacts of that, and that gives justification for going out and getting the good data or demonstrating to regulators or governments that that data should be collected for future analysis.
Yeah. And often one of the things, we shouldn't forget this as well. One of the things that models can do, develop a model to try to answer a particular question or meet a particular need. Actually, by doing the modeling, it reveals the next question.
Yeah.
And that's perfectly fine. And one of those things or one of the next action, which might be, oh, look, we need to go out and collect this data. We need to monitor X, Y, or Z. It's a really interesting question that's just come up. I think, hopefully, there's a few questions to do with data and uncertainty, which we've talked around. So one that's just come up, I think, on the IPCC report on global warming, and the question, what is the level of primary demand that should be achieved or reached to achieve the goals? So, I think this is one of the ways in which models are being used by policymakers, is because there are different options, there are different pathways. So one pathway, for example, we might invest a lot of time, effort, money in reducing that energy demand, meeting that end service with less energy. So in other words, improving energy efficiency, or actually some of the energy services might change. So, mobility, how many passenger kilometers are there going to be anyway? So energy efficiency is one part of it. Each passenger kilometer is served with fewer kilowatt hours, but do they have to have that many passenger kilometers in the first place? I think we've seen some hints about this during the COVID lockdowns in many places, where lots of us have been working from home. Emissions to do with transport have reduced dramatically, although they're now on the way back. And people are very uncomfortable about public transport, so it's a big challenge. But that compares with effort on the demand side compares with effort on the supply side. Where do we get all this low carbon energy from? And it's not always obvious over these kind of 2 or 3 decade timescales what the kind of most cost effective pathways are going to be, and which ones are kind of most risky if they're very dependent on behavioral change that we can't be confident of achieving, or very dependent on some technological change that is not yet there.
And I'd add to that this is one of the reasons why I highlight the importance of separating out carrier demands for energy and actual energy services. We have some work coming out shortly which demonstrates that if you take people in the UK who are currently heating their homes directly with electricity and replace it with heat pumps, then their demand for actual energy could potentially double, because you have a rebound effect. You're not just giving them lower carbon electricity, but also potentially cheaper electricity, and they'll just use more of it. So this becomes an important thing to understand, the level of rebound that you might get as you change the system. Demand will not be a constant, and hence don't just assume it's a fixed exogenous variable.
So I think it's time to wrap up. It's been really good conversations. I'm also happy to see a few questions there.
Yeah, we answered. I think we're time to wrap up. I'm just going to mention very briefly, Pierluigi. There's a couple of answers I typed in. So if you go into the Q&A panel, I've tried to answer a couple of them. We've talked about ones maybe not in a great deal of depth, but with a lot of kind of, here's the recipe for how to deal with uncertainty. There would be kind of stochastic methods that can maybe help in this, but I think uncertainty on the inputs is something that we've talked about, and at least to be open about the nature of uncertainty. There was one more detailed question about refrigeration and refrigerant gases, so maybe we'll leave that for you, Pierluigi, to pick up if that comes as part of your presentation, or Alex's later on.
Yeah, we also have a discussion later in the afternoon anyway, in case. But yeah, so I would like to thank you again, Keith and Graeme. Really good. Now we have about 15 minutes of break, and then it will be Alex's turn, who will present multi-energy power flow and multi-energy optional power flow. So stay tuned, everyone. We'll be back.
Yeah, I think probably stay logged in. You can probably, just go away, do what you need to do, and come back. And
fill your cups.
Yeah,
great.
But thanks again, both, and thanks everyone for the questions. Cheers.
Thank you.